Welcome to today's webinar, Advancing Rotating Detonation Engine Using CFD, brought to you by Converge Science. Thank you for joining us today for the fifth installment of the 2024 Converge webinar series. My name is Matthias Sulis and I'm part of the business development team at Converge Science. I will be your host for today's event. I'm glad I can be here with you today and learn about the tools that Converge CFD software offers to model RDEs. Converge Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, Angela Hu. Angela Wu is a research engineer at Converge Science. She earned her Master's of Science from California State University, Los Angeles, and her PhD in Mechanical Engineering from the University of Michigan, Ann Arbor. After her PhD, she did a postdoc at Sandia National Laboratories before joining Converge Science. Her research expertise is in internal combustion engine, turbulent combustion, LES modeling, and conjugate heat transfer. Without any further delay, I will now pass the ball to Angela. Thank you all.
All right, thank you, Mattia. Welcome, everyone. I am a research engineer at the Michigan branch of Converge Science, and today I will be talking to you about rotating detonation engines and using Converge CFD to advance their technology. So let's start first with a brief history of rotating detonation engines, or RDEs. In the 1950s, detonation as a means of propulsion was conceptualized by James Nichols at the University of Michigan, who built and tested a pulse detonation engine, or PDE. In 1960, Wojciechowski demonstrated the first continuously rotating detonation wave in the USSR. Nichols continued to apply theoretical and experimental research into RDEs for rocket propulsion, as did Adamson and Olson. And from then on, it was quiet on the research front until the 2000s, where there is an increased activity into RDEs. For example, in 2005, an RDE patent was issued to Akihiro Tobita from Mitsubishi, Toshida Fujiwara from Nagoya University, and Peter Olansky from Warsaw University of Technology. In 2008, the Air Force Research Lab, or AFRL, built the world's first manned pulse detonation powered aircraft, as shown in this image on the top of the Long Easy aircraft. And then in 2021, a sounding rocket from Japan Aerospace Exploration Agency, JAXA, was powered by an RDE for 6 seconds above Earth, acting as a second stage of propulsion, which you can see here in the bottom image. In 2021, the Warsaw Institute of Aviation performed the first successful flight test of an experimental rocket with an RDE powered by liquid propellants for about 3.2 seconds. In 2023, Beijing Power Machinery Institute demonstrated a hybrid air-breathing engine with RDE for propulsion at below Mach 7 and an oblique detonation engine up to Mach 16. In 2023 as well, an RDE drone flight was achieved in China, developed by Chongqing University and thrust-to-weight ratio engine company. Let's take a look at ramjets, scramjets, and pulse detonation engines. Ramjets is a form of air-breathing jet engine with no moving parts compared to turbojets. It uses the forward momentum of the aircraft to compress incoming air to high pressure. The fuel is then injected into the combustion chamber, resulting in subsonic combustion. And then the hot exhaust gases passes through the nozzle, which increases velocity and produces thrust. It operates in the 2 to 6 Mach range, and they're very inefficient until airspeeds above 620 miles per hour due to low compression ratio, so it requires an additional type of propulsion. Scramjets are very similar to ramjets, but the combustion happens in the supersonic regime. It operates in the 5 to 25 Mach range, and again, it requires additional type of propulsion to accelerate it from 0 to about Mach 4. It's a very challenging problem to achieve this type of propulsion since it's challenging to achieve sustained operation, and hypersonic flight generates a lot of drag and heat. Pulse detonation engine uses detonation wave, which increases thermal efficiency due to rapid compression of the mixtures to high pressure and temperatures. It operates in the 0 to 4 Mach range, so it can be used to bridge the gap between subsonic and hypersonic regimes. The thrust is proportional to detonation frequency, and detonation combustion can happen through either direct initiation or from deflagration to detonation transition. So the main challenges are the very large amounts of energy required for direct initiation, or if you're using DDT, you need a long enough combustion chamber to achieve detonation. And PDEs also require repeated initiation of the detonation. In addition, the timing and control of fresh reactants into the chamber is very hard, and it has a very limited operating frequency. So this is where rotating detonations come in. RDEs are essentially detonation-based combustion devices which achieve higher thermal efficiency due to using detonation. There are no moving parts, and the engine can be made very compact. The combustible mixture is injected axially through the nozzles, and once ignition is initiated, a continuously moving detonation wave or waves propagate azimuthally around the combustion chamber, as you can see from the movie. It does not require purging of gases after each pulse like PDEs do, and it can offer a steady source of thrust at high frequency once the detonation wave is established. It is well suited for hypersonic aircraft or rocket propulsion, and also for stationary power generation. CFD plays an important role in RDE development. This is complementary to experiments where the engine encounters harsh operating conditions and certain measurements cannot always be achieved due to current measurement capabilities. CFD allows for fundamental understanding of the combustion and wave dynamics of RDEs, and we can test many different operating conditions as well as optimize the design for performance enhancement. So why should you use Converge for RDE simulations? Converge CFD has the capability of very accurate combustion simulation using our SAGE detailed chemistry solver, which you can also activate in regions where combustion is important to reduce computational expense. We have detailed reaction mechanisms through the Computational Chemistry Consortium, or C3, which include PAH and NOx chemistry, and tools for generating surrogate and multi-fuel mechanisms, including jet fuels. The code is highly scalable, as shown in the core versus speed up plot on the top right here for Sandia Flame D, where the simulations were performed on the Blue Waters HPC at the University of Illinois. Below is another speed up plot, but this time it's the scaling performed for the RDE simulations. So you can see that we are actually achieving a very good speed up compared to an ideal case. Our code also does not require any meshing from the user. The mesh is created during runtime automatically. We also have Adaptive Mesh Refinement, or AMR, capability for variables like pressure, density, and velocity. And this is very important as there is a wide range of scales in RDEs. For example, detonation cell width is about 1 to 1,000 millimeters. For example, with hydrogen-air combustion, the detonation cell measures about 10 millimeter at an equivalence ratio of 1. Nozzle diameters being about 1 millimeter, annulus width 5 millimeter, channel height 50, and detonation tubes being about 400 millimeter. So to resolve this with a fixed grid requires a very fine grid, and instead we can use a Corsair-based grid and use the Adaptive Mesh Refinement capability to add self-refinement where needed. We also have high-fidelity RANS and LES models, and the muscle scheme for accurate simulations with shock, discontinuities, and large gradients. Our software can handle both premix and non-premix combustion, and we also have spray models available in case you need liquid parcel injection. And ignition can be modeled through our source modeling capabilities or using appropriate initial conditions. So let's switch gears a little and talk about the differences between deflagration and detonation. Deflagration is combustion in the subsonic regime, where essentially Mach is less than 1, and pressure waves in front of the flame travels through the unburned mixture at the speed of sound, while the reaction front, or the flame front, is further behind it, traveling at velocities slower than the speed of sound. The propagation of the flame front is controlled by transport processes and chemical kinetics, and flame speeds are approximately 1 to 100 meters per second. And in case of deflagration, the pressure decreases across the deflagration. So P2 in the unburned mixture is lower than P1. In contrast, detonation is combustion in the supersonic regime with Mach larger than 1. The pressure wave travels through the unburned mixtures at speeds greater than the speed of sound. The flame front is right behind the pressure wave, which energizes the shock wave. The propagation is then controlled by the shock waves, with flame speeds reaching about 2,000 meters per second. And pressures increases across the detonation with P2 greater than P1 as the shock compresses the unburned mixture. So how do we initiate detonation? We can do direct initiation, which requires a high energy source to drive a sufficiently strong enough blast wave, so it's directly responsible for initiating detonation, but this requires a very large amount of energy. Or we can do what's called deflagration to detonation transition, or DDT, which is essentially combustion that starts out as a deflagration with a relatively weak ignition source. And as the flame develops and becomes increasingly turbulent, it accelerates until a shock wave is formed. This requires time, and the combustion chamber has to be long enough for turbulent mixing to develop into detonation. So DDT was studied previously in a blocked channel using Converge CFD. The significance of DDT is, first of all, safety, such as storage of fuels or explosive mixtures in mining, in pipelines, and also it is used as a way to initiate detonation devices such as PDEs and RDEs. There are significant challenges to this type of simulation, including a wide range of length scales from 4 to 10 orders of magnitude, and nonlinear interactions between flames, shock, turbulence, and boundary layer. So to study this problem, we developed a 2D simulation with obstructed channel for a controlled numerical study of various stages of DDT. This is to first understand the evolution of the flame and flow field and how to create the right conditions for detonation. We also want to understand and control the transition to detonation and how to propagate and sustain detonation wave through the unburned mixture. So on the right, you can see two types of channels. One is just half of the channel with obstructions on just one side of the channels with some height and thickness. This is known as the unstaggered configuration, and what we do is we control the blockage ratio. The flame is initiated on the top left corner with some ignition source, and combustion then proceeds into the unburned mixture. And you can see that it's a very long channel. The second configuration is the staggered block configuration, where again combustion is initiated on the left side and allowed to propagate through the unburned mixture. And what we can see is that there are blockages that are staggered on the top and bottom. What we vary here is the blockage ratio, so the height of these blockages, as well as how far apart the stagger of these channels are, of these blockages are. So for the simulation, the physical models are as follows. For turbulence, we are using the dynamic Smagorinsky LES model. For combustion, we are using the SAGE finite rate detailed chemistry approach. The mechanism for hydrogen combustion contains 10 species and 21 reactions from Conner et al. The mesh settings are as follows. The base mesh is 2.5 millimeters, and we will use AMR for velocity, temperature, pressure, and OH, so that the minimum cell size that is achieved is about 78 microns, which allows us to capture the detonation front as shown in the figure below here. So this is the progress of the flame front as time goes on. And you can see that as the flame develops, it becomes more and more turbulent and corrugated due to the interactions with the blockages, leading to increasingly faster flame speeds and developing into a detonation flame front. So these two videos here show you the differences in flame evolutions with 25% stagger and 50% blockage on the left, and 50% stagger and 75% blockage on the right. What you can see is that the simulation on the right, which has the higher blockage as well as 50% stagger, develops into a turbulent flame much faster than the simulation on the left, leading to faster deflagration to detonation transition. The simulation on the left still develops into detonation, but it does require a longer time as well as a longer channel length to transition to detonation. So for different stagger and blockage ratios, the flame acceleration appears to be clustered. Each cluster corresponds to the same blockage ratio, but different stagger ratios. And the inferences that we can take from this study is that the flame acceleration is strongly correlated to the blockage percentages, but there's a weak correlation or almost no correlation existing between flame acceleration and stagger ratio. This table here shows you the time it takes for detonation to be achieved from deflagration for the different blockage ratios and stagger ratios. And one case actually did not achieve any detonation. As the blockage ratio increases for each stagger ratio, you can see how the transition is happening in less time. We have also done investigations into deflagration to detonation transition using simulations with detailed chemistry for inhomogeneous and homogeneous hydrogen-air mixtures and validated against experimental results. You can see that on the right here, where experiments are in the black symbols. The simulations performed by the experimental researcher is the gray line, and the Converge simulations are in red. You can see that we achieve very similar results compared to the experimental as well as the previous numerical simulations. So I did mention the Computational Chemistry Consortium, or C3, from which we can have mechanisms for a whole bunch of different fuels, including hydrogen, methane, and other fuels that are important for RDEs. So we have validated the C3 mechanism for to see if they achieve the Chapman-Jugay flame speeds using 3D simulations of a detonation tube. So the detonation tube is shown here very simply. It has adiabatic slip walls with Dirichlet pressure and Neumann velocities at the outflow. The initial mixture contains a stoichiometric mixture of the fuel and air or oxidizer at a constant temperature, and different pressures were simulated. A short ignition source was used to initiate the combustion, and the flame is then allowed to travel along the tube until the deflagration to detonation transition happens. We use the LES Dynamics Margarinsky model for subgrid scale modeling. The base grid is about 0.375 millimeter, and we did use velocity and temperature AMR so that the smallest cell size is about 0.18 millimeters. And we compared our flame speed results against the CJ velocity obtained from a NASA C-Run calculator. So here I'm showing you two different validations, one for hydrogen air and another for methane-oxygen. The CJ velocity from NASA is in blue for both simulations. The C3 mechanism velocity is shown in red. And we also compared another mechanism that is typically used. So for example, for hydrogen air, we use the Con-Air mechanism that's shown in yellow here. And for the methane oxygen, we are using the Shu mechanism in yellow. We also tested 5 different initial pressures from 1 to 5 atmosphere. And if you look at the hydrogen air combustion simulation, you can see that at low pressures, we underpredict the CJ velocities, whereas at high pressures, the C3 mechanism and the Con-Air mechanism overpredicts the flame speed. And this can be due to many different reasons, including grid resolution, as we did not perform a grid study for the simulation. That can be one area of improvement. In terms of the methane-oxygen simulation, where again, the C3 mechanism underpredicts the flame speed at lower pressures, and at higher pressures, we overpredict the flame speed. But compared to the Shu mechanism, the C3 mechanism is actually predicting a more accurate velocities on the low pressure side. So using this result, we can confidently say that we can use the C3 mechanism in our RDE simulations. Right. In terms of supersonic simulations, we have performed them in Converge CFD for hydrogen in vitiated airstream. The computational domain looks as follows. The vitiated air is coming in on the left at inflow boundary condition of 1260 Kelvin for temperature, and at a high inlet velocity of 2.44 Mach. It's exiting on the right with outflow boundary conditions, with Neumann outflow boundary conditions. The walls are cold and no slip is applied, and 100% hydrogen is introduced from the bottom of the computational domain at 0.13 Mach and at about 300 kelvins. Combustion is simulated with SAGE detail chemistry, turbulence with Rand's RNGK epsilon model, and a 4 millimeter base grid was used with level 3 AMR. Results of H2O species by volume fraction was compared at a specific location close to the outlet for different Y values. And you can see that compared to measurements, which is shown in black, our results with SAGE, shown in blue, compares very well in contrast with the equilibrium model that is shown in red here, which is performed by the original authors. So we can see that supersonic combustion can be simulated in vitiated airstreams in our code. We have also created a 2D RDE model, which is essentially an unwrapped version of our 3D RDEs. This is good for quick simulations where you want to vary operating conditions, optimize solver settings, do grid sensitivity studies, and change the fuel without having the need to do expensive 3D simulations until you need to do them. So for this simulation, we use the LES2 equation K epsilon model. Again, we use detailed kinetic mechanism for hydrogen air with which is extracted from the C3, the full C3 mechanism with 12 species and 37 reactions. We use the finite rate stage detailed chemistry solver for combustion modeling. We also used adaptive mesh refinement for velocity, temperature, and OH gradients for trade-off between accuracy and computational expense, and performed a grid sensitivity study by varying the base mesh and minimum mesh grid sizes. Periodic boundary conditions were applied to the left and right of the boundaries, and 2D boundary conditions to the front and back of the computational domain. To initialize ignition, we use a region-based initialization with hot and high pressure gases in the ignition zone and cold and low pressure gases in the pre-ignition zone. And what this does is allow the detonation front to develop with a very sharp pressure gradient at the area where these two regions meet. And fresh fuel-air mixture is flowing in continuously from the bottom in the nozzle region. So here are the results of the final 2D simulations. A single wave develops and it takes about 1 millisecond to reach steady state, as can be seen from the pressure profile on the top here, which is the pressure in the ignition zone. This type of initialization works well for hydrogen-air mixture detonation. The wave speed reaches approximately 1668 meters per second, and peak cell count in the simulation is about 400,000. The simulation took about 43 hours on 4 cores for a 3 millisecond run, and this example case is available in Converge Studio for you to play around with. Moving on from the 2D simulations to 3D simulations, we demonstrate the AFRL Hydrogen-Air RDE, which was performed by Pinaki Pell at Argonne National Lab. The experimental setup of this engine contains a pre-detonator tube where ignition is initiated, and also high frequency and low frequency pressure transducers at different locations, which provides data for comparison against the numerical results. Fuel and air are introduced into the system separately from the bottom of the RDE through 120 fuel ports and then exhausted at the top. And this table provides some dimension information of the RDE itself. And again, the fuel is hydrogen. So you can see the computational domain of the RDE with the same pre-detonator tube as the experiment, the 120 fuel ports that you see, the air inlet, and the RDE annulus. A spark is used to ignite the fuel-air mixture in the pre-detonator tube. They use the unsteady RANS realizable K-epsilon model to model the turbulent flow, detailed kinetic model for hydrogen-air chemistry with 9 species and 21 reactions, which was first tested for simple 1D detonation simulations. They use the SAGE finite rate chemistry model for combustion. And again, AMR is used for velocity, temperature, and density gradients for trade-off between accuracy and computational time. A grid sensitivity was also performed, and they simulated 3 different cases where they vary the airflow and the fuel flow rates, leading to approximately equal global equivalence ratio of 1 for all 3 cases. And these 3 cases have different number of waves as was found in the experiment. So the simulation results is shown here in this animation. The pre-detonator tube helps to ignite the fuel-air mixtures coming in from the bottom of the RDE. And as the detonation wave develops and traverses the annulus, fresh fuel and air is coming in from the inflow boundaries below, and allowing the detonation wave to be sustained through the simulation. They compared the static pressures for cases 1 and 2 against experiments, which is shown in the solid lines. And you can see that they got really good results with about 4 to 10% error in accuracy. It was also a low-cost simulation as it only took them about 48 hours on 144 processors. And comparing to experimental wave frequency, wave height, fill height, and oblique shock angles, they were all within experimental uncertainty, except for perhaps case number 2 for the oblique shock angle, which was much lower than the experimental value. Mode transition in hydrogen RDE was also studied using unsteady RANS and SAGE detailed chemistry solver. Essentially, any changes in inlet conditions such as pressure, mass flow rates, or fuel reactivity can lead to abrupt changes in number of detonation waves in an RDE, which is known as mode transition. So if you look at these video here, if I start it over, you can see that there is a single wave traveling, but then at some point there is a second micro detonation happening, which results from interaction of burnt products with fresh mixtures that leads to essentially mode transition from 1 to 2 detonation waves. So you can see that there's now 2 detonation waves traversing the combustion chamber. High-fidelity LES has also been used to model RDEs with hydrogen-air mixtures. Here, a wall-modeled LES framework was used using the dynamic structure subgrid model for an RDE. The peak cell count, since this is an LES simulation, was about 19 million, and runtime was about 36 hours on 500 processors per millisecond of the simulation time. In this simulation, a single wave develops in the RDE. Snapshots are shown on the top here for temperature, pressures, and density. And you can see that they identify the different areas of the shock and combustion regions in the plots above. Now, when compared to experiment, LES seems to be more accurate than the RANS in this case setup, achieving very good results for wave frequency, wave height, fill height, and oblique shock angle. It was overestimating the channel pressure at a certain location compared to the unsteady RAN simulation, but this can just be due to spatial distribution of the pressures being a little different. Okay. RDE simulations with ethylene-air were also performed by Argonne National Lab. This RDE contains, again, a pre-detonator tube, the fuel inlet ports, an air plenum, and a spark source, which was used to initiate the detonation. Let's start over. RDE simulations with ethylene-air were also performed by Argonne National Lab. The RDE contains a pre-detonator tube, fuel inlet ports, an air plenum, and a spark source was used to initiate detonation. 3 different air mass flow rates were used to vary the global equivalence ratio slightly. And the mechanism for ethylene-air contains about 22 species and 38 reactions using a reduced chemistry. The peak cell count was about 28 million, and it took about 48 hours on 500 processors per millisecond of simulation time. What they found was essentially a weak lifted azimuthal wave due to delays in mixing and reactions. There is a high temperature zone that trails behind the azimuthal waves, as you can see here, which constitutes commensal combustion. This is essentially unwanted or secondary combustion behind the detonation waves. Another form of secondary combustion is the parasitic combustion that happens in front of the detonation wave in the refill zone. And this simulation achieved about wave speeds of 52 to 53% of the corresponding ideal CJ speeds, which could not be captured using unsteady RANs. So compared to experiments, the simulations are slightly under-predicting the wave speeds for the three cases, and very slightly under-predicting the liftoff height and the wave height for cases 2 and 3. Finally, high-fidelity LES of the AFRL methane-oxygen RDE was also performed by Argonne National Lab. And you can see here a detailed schematic of the cut section of the RDE, essentially lying on its side with a zoomed in section of the fuel and oxygen injectors. The methane oxygen mechanism used is a reduced mechanism with 12 species and 37 reactions, with peak cell count of about 18 million, requiring about 48 hours on 500 processors per millisecond of simulation time. A detailed investigation of the fill region and injector dynamics was performed in the simulation, and 3 fuel flow rates and oxygen flow rates were tested for 2 different global equivalence ratios. Now, as can be seen from this animation, if it's playing, as can be seen from the animation, mode transition occurs in the simulation where essentially one wave develops into 2 waves due to micro detonations and interactions of the large combustion structures. They were able to achieve good comparisons with experimental data for the 3 cases, the baseline, high equivalence ratio case, and high mass flow rate case. So they were able to achieve the correct number of waves and very close pressure values to the experiment, which is CTAP 1 and 2. The wave speeds, if you compare them to experiments, are underpredicted, but the amount of thrust that they were able to obtain from the simulations were very close to the experimental values. So in summary, Converge is a very powerful CFD tool for modeling RDEs. It has several features that are useful for RDE simulations, including AMR based on velocity, temperature, and/or species, inlet meshing capability if needed, scalability, high-fidelity RANS and LES models, and fully coupled detailed chemistry solver. Converge can capture accurate combustion dynamics of RDEs using high-fidelity modeling approaches. Both air-breathing and rocket RDE configurations with a variety of fuels, hydrogen, ethylene, and methane, have been simulated using Converge, and these simulations were validated against experimental data and accurately capture the detonation wave characteristics with high predictive accuracy. And we're continuing to validate our feature and improve our case setup recommendations for RDEs. So with that, I want to thank you for your time and attention to this webinar about rotating detonation engines.